Today's webinar, we will discuss on structural optimization of steel structures using pre-engineering. As most of you all probably know that there are lots of steel structures coming up in our country right now. And there's a lot of factors behind the rapid expansion of steel structural buildings in the country. So we will see all these things and also why we need to have an efficient design for the best economical steel structures to come up in the country, so that we have lots of like opportunities towards designing. So with that, I'll just begin the slides. So today's webinar, we have we'll take you through the overview of the steel structures, the market trends, the fundamentals, the codes and standards that we follow, the software that we use in the industry, the optimization techniques. I'll just give you a brief on the optimization techniques, then concept of pre-engineered buildings and pre-engineered buildings versus conventional buildings and its job prospects. So here we will also do a case study to understand how efficient a pre-engineered concept is. So steel structures became popular in the 20th century. Before that, it was very rare to have steel structures. As you all know, the steel structures are mostly used in bridges, towers, stadiums, or industrial buildings. That is, wherever you need a large span, you can see steel buildings. So they have like high strength to weight ratios, and they are very lightweight structures. So if you can see, there is a if you have a 1 inch of steel rod, that is a 25 steel rod, it can hang almost 20,000 kg or 20 tons of weight. That is almost equivalent to 4 elephants. So that is the strength of steel compared to its weight. So that is the greatest advantage of having steel structures for large spans. In concrete, you may be going for a 3 to 6 meter span, but in steel structures, you can see around 30 meters, 40 meters without an intermediate column. Then it has good ductility and fatigue strengths. So any cycle loadings can be easily taken up by the steel structures. So it's a very rare phenomenon that the steel structures fail rapidly. So in concrete structures, if you can see, there will be cracks in the structure, but as you see in steel structures, you don't have that kind of issue like crack because it is ductile. It can sway, it will bend, it forms according to the sway or the load. Then the prefabrication and mass production is possible. So there is only lesser construction time for it. So if you want a particular product, it's just like buying a product. You want a particular steel building, you have this area. So it can be readily made in the fabricator's unit and brought to the site and constructed in no time. And it can be strengthened or retrofitted easily. So once you see that, okay, there is some issue with your steel structure, it is very simple and easy to retrofit it. So that is another advantage of having steel structures. Then the reusability and recycling. So maybe after a couple of years, you don't want that structure to be there. You have some other idea. So you can take the whole structure and put it in somewhere else. So that is the greatest advantage, I would say, for steel structures. And all the members can be recycled into any other forms or shapes or for any other elements. So some of the famous steel structures that we have, the Sardar Vallabhbhai Patel statue or the Statue of Unity, Statue of Liberty. See, all these things are primarily formed from steel skeleton, and then they have copper facades. Then we have the Beijing National Stadium or the Bird's Nest Stadium. Then the Eiffel Tower, then the Pamban Bridge or the Taipei Tower. So these are a few of the famous structures that we all know. And there are many other structures, mostly industrial buildings. If you are coming from any industrial areas, you can see there are lots of buildings, warehouses, or factories made from steel structures. So let's see the market trends, how the market is behaving right now. So there are lots of industries that use steel buildings, like manufacturing, power and energy, construction, oil and gas, etc. So basically all kind of industrial buildings where you need a large span without much of an obstruction, you can find steel buildings. Oil and gas for pipe racks or any other conveying structures, you can find steel structures being used. The Indian structural steel fabrication market is expected to register a compound annual growth rate of 5.5% over the next 5 years. And the global manufacturing companies' focus to diversify production units outside China is expected to drive India's manufacturing sector to grow more than 6 times by 2025, that is to around 1 trillion US dollars. So with the COVID-19 scenarios, many companies are planning to shift their base to other cheaper alternatives like India. So we have lots of opportunities coming up in the next few years. Then there are lots of government initiatives like the metro stations, airports, smart housing, smart cities, industry corridors, power plants, ports, other infrastructure developments, which will be basically needed if we have to be a manufacturing hub. These are also expected to drive the growth of structural steel building sector. Now let's see the components of industrial steel building. So some of you already know this, but for others who are freshers, we'll just see. You can see this is the main frame that we have in a industrial building. So any intermediate frame where the maximum loads come, that would be the main frame. So these members, the beams which form the roof beam, that is called rafter, and the green members which run parallel to the length, which supports the roofing sheet, they are called purlins. So purlins can be call form members like Z sections or channel sections, or even hot roll members. We'll see what is hot rolled and what is call formed in the coming slides. But these are the purlins are basically members which support roofing sheets. Then you have the bracings. So bracings are required for the lateral stability system. So when you have any lateral load, like say, for example, wind or seismic, you need to have a lateral stability system so that your structure is stable. So unlike concrete structures wherein all your joints are fixed, like hope you all are from the civil background and you guys know the fixed supports and pin supports. If everything is fixed support, you may not need a bracing system. But in case of a steel building, you achieve rigidity along the width of the frame, and a lateral stability system is required along the length. So bracings are provided along the length. So the bracings can be of different types. Either it can be X bracings or A bracings, inverted A or K bracings. There are lots of types of lateral stability system that we come across. Here in this figure, we have X bracings. So X bracings can be steel, rod, or anything. So any member which can take tension or sometimes compression. The height to the eave. Eave is the bottom of your rafters. That is called eave height. Then you have the end wall post. This will be supporting your this one, like the door jambs, as well as it will be acting like a wind post. So wind post is something like here you need to have on this face, you need to have supports for your wall sheet. So for those things, you need to have a column. So these columns are called wind post or end wall post. If you can see, these rafters are smaller than what you can see in the main frame. This is because only half the load is coming to this rafter. And in the future, there may not be a plan to extend this particular frame to this area. Now, these are all self-explanatory terms: overhead door jamb, door header, then end wall corner columns, end wall rafter, door jamb, window frame, wall bracings, the bracings for the lateral stability system on your walls. And these will be the columns. So here you can see the columns are tapering. It has a lesser depth at the bottom and a higher depth at the top. So we'll see why this is that way. Then these are called girds, these members. The members are called girds because they support the wall sheets. They are just like the purlins, but on the walls. That's the only difference. Then the distance between the two intermediate columns is called the bay spacing. So this will be the interior bay, the end wall bay. So this is all about the components of industrial steel building. Now the type of sections commonly used For columns, it can be I sections or any built-up laced or batten columns or hollow steel sections. Rafters also again I sections or built up. It can be truss as well. But in this webinar, we are not discussing about truss. Then purlins and girds can be call-formed sections. So call-formed sections are lightweight members. So that will be carrying the lightweight roof sheets or any insulation panels. So that can be channels or Z or hollow steel sections. Then eave strut. Eave strut is the one given at the eave. If we go back to the previous slide, this member is the eave strut, the blue one. This is given at the eave of the building. So this will support the rain gutters as well, and also any sag roads that may come from the walls. So sag roads are nothing but members which will restrain your girds or purlins. So that is not shown in this figure right now, but there can be members if the length is high. So that is the function of eave strut. Then we have the bracings. Bracings can be rod, pipes, or angles depending on if whether it is a tension only bracing or tension and compression taking member. So if it's a tension only member, then there won't be any compression. It will simply buckle in compression. So simple rods will be fine for bracings. We already discussed sag roads. So just moving to the next slide. Mechanical properties of steel as per IS 800 2007. So this may vary depending on code. Slight changes might be there depending on codes, but mostly all the codes follow somewhat similar values. So density 7,850 kg per meter cube. Modulus of elasticity 200,000 Newton per mm square. Grade of steel can be mild steel, that is E250, or where its yield strength is 250 Newton per mm square, or a high strength steel where its yield strength is 350 Newton per mm square. Then the Poisson's ratio is 0.3. Coefficient of thermal expansion is 1.2 times 10 raised to minus 6 per degree Celsius. Now let's see the difference between hot rolled and cold rolled steel or cold form steel, which I mentioned for purlins or girds. So hot rolled steel, hot rolling is a mill process which involves rolling the steel at a high temperature, typically at a temperature over 1000 degree Fahrenheit, which is above the steel's recrystallization temperature. When steel is above the recrystallization temperature, it can be shaped and formed easily, and the steel can be made in much larger sizes. So almost all the sections that we have learned in our textbooks like ISMB 500, ISMC, or ISHB, all these things are hot rolled sections. And hot rolled sections are typically cheaper than the cold rolled steel due to the fact that it is often manufactured without any delays in the process, as the reheating of the steel is not required as it is with the cold rolled. We will see what is cold rolled steel. When the steel cools off, it will shrink slightly, thus giving less control on the size and shape of the finished product when compared to cold rolled. So if you remember the section sizes of ISMB 300 or 400 or 500, you can see the web thickness can be 8 mm, 10 mm, 12 mm kind of, and your flange thickness can be even more than 15 mm. So hot rolled steel, the member sizes, the plate thicknesses will be high. So you have a lesser control on the accuracy of your members. So it may not be sharp, or like there can be some small tolerance differences in the hot rolled steel. So in order to achieve this perfection, we go for cold rolled steel. Cold rolled steel is essentially hot rolled steel itself that has had further processing. The steel is processed further in cold reduction mills, where the material is cooled, followed by annealing or timbers rolling. This process will produce steel with closer dimensional tolerances and a wider range of surface finishes. All cold products provide a superior surface finish and are superior in tolerance, concentricity, and straightness when compared to hot rolled. So almost, if you see any cold form section, the thickness will be 2 mm, 3 mm, 4 mm kind of, because you can achieve as a very good tolerance and the straightness. So the cost of cold rolled steel is also high. So we normally use these cold rolled steel for secondary members like purlins or girds, and hot roll members for larger columns and beams. Now let's see the applications of hot rolled and cold rolled steels. Hot rolled steel is used in situations where precise shapes and tolerances are not required, like in columns and beams. Applications of cold rolled steel, any project where tolerance, surface condition, concentricity, and straightness are the major factors, like roof and wall systems. So these will be lightweight. So you can save a lot of money on your roof and wall systems as well, because the load is quite low. You can use call form sections, and they are lightweight and they have very good surface finishes. The codes and standards that we follow for the design of steel structures. Basically, in India, we follow IS 800 2007, which is the code of practice for general construction in steel. So IS 800 2007 is a limit state method code. It also has working stress method clauses as well. But as per the latest methodology, we follow limit state method. IS 808 1989, which gives the dimensions for hot rolled steel beam, columns, channels, or angle sections. IS 811 1987, specification for colform light gauge structural steel sections. Then there is a code named MBMA code, or Metal Building Manufacturers Association code, which is basically an American standard that has been brought forward by the Metal Building Manufacturers Association, which mostly look into pre-engineered buildings. AISC 360, which is a specification for structural steel buildings as per American standard. The next one is the Eurocode EN 1993 Part 1, General Rules and Rules for Buildings. So Eurocode has lots of sub codes for steel structures as well. American standard as well has a lot of special documents to be referred along with the normal code. Now let's see the softwares that we normally use in the industry. The most common software used in India is StatPro. Then in the Europe and the Middle East, Robot Autodesk. In Middle East, StatPro is also very common. Mostly people work on StatPro, but when it comes to like good finite element analysis, you may go for Autodesk Robot. Then we have ETABS, but ETABS, although rarely used, some people and some company use ETAB software because it is more familiar to people who have used concrete design. Then SAP 2000 is a very good software for plate elements especially, and that's a very good finite element tool coming from the same parent company of ETABS. Then Tekla Structural Designer, it's a comparatively new software, is also a wonderful software based on the experience. Now let's see what is optimization. So our webinar is all about structural optimization of steel structures. So we need to understand what is optimization before we go into the structural optimization. So weight of a steel structure is a major component of the total cost. The minimization of the cost should be the final objective for optimum use of available resources. So maybe in concrete you say in volume, but in steel you say in tons or weight of the steel structure. Now, the total cost of a steel structure will include the material cost of the structural members, such as beams, columns, and bracings, that is a weight. The fabrication cost, including the material cost of connection elements, bolt, electrodes, and the labor cost. Steel structures require highly skilled labor, so the labor cost can be quite high. The cost of transporting the fabricated pieces to the construction field. Unlike concrete, steel structures may not be always fabricated at the site. You may be doing it at a factory or any other fabrication units and bringing it to the site. So the transportation cost is also a factor. Then you have the erection cost, including the material cost of connection elements, bolt, electrodes, and the labor cost. So for the erection, you may need cranes for the erection and special laborer for erections. So that will all add to the total cost of a steel structure. If you need to optimize a steel structure, you should have an efficient planning of the building system using higher grade steel, reducing splices, and we will see what are pre-engineered buildings. That is a wonderful optimization method that has been brought forward by some of the greatest engineers in the US. So we should not only focus on weight of a building in a steel structure. You should also focus on some of the planning members, because sometimes your trailer size, which can transport your fabricated member to the site, can be 6 meter long. 6 meter long trailers are very common in India. If you are designing a member for 12 meters, maybe it's quite difficult to transport it from the fabrication unit to the site, because you may not get a 12 meters long. So planning of the building system, how you want to plan it, how you will place a crane, how you will lift it. So all these things come into optimization. But here in this webinar, we are more commonly looking into the pre-engineered concept, where a design engineer can contribute to the optimization.